now that we've walked through intermolecular forces and evaluating the strength of the intermolecular forces in a sample, let's look at how this applies to different states of matter. And our states of matter are gas, liquids, and solids. And looking at these different types of phases, our gas particles will be far apart from one another. Our liquid particles will be really close and constantly moving around. And our solid particles will not move and be arranged in a very orderly manner. And so we have an increase as we think about going from solids to gases in motion. And increasing motion really comes from a higher average kinetic energy. So kinetic energy is that energy of motion that we discussed, which is different than potential energy, which is energy stored in a chemical bond. So as this increases, things are going to increase how much they move. And so we have gas particles moving a lot and solid particles not. And our gas particles are further away from each other and our solid particles are closer together. And so if we want to think about intermolecular forces and how they apply in this situation, it means that the effect of intermolecular forces, so that effect of them on the physical properties that a sample demonstrates, is going to really affect our solids, right? Because these IMFs won't change at all. And in our liquids, it'll be a little bit less important, though very important still. And so because they're close to one another, IMFs will constantly exist, but the IMFs will always be changing. So that's because the location of a particle will change in a liquid where it won't in a solid. And gas particles, they're going to have just no effect because they're so far apart from one another. And so we can evaluate the properties of these different phases by kind of lumping these into two categories. Liquids and solids will consider IMFs, and they'll play a huge role in how they behave. And gases will all behave the same. So the chemical identity will not affect the behavior of a gas, but it will affect the intermolecular forces, and so the behavior of liquids and solids. There we go. And so here's a nice summary of our different states of matter. We can think about this now with an IMF lens. Our gas state right here, our gas fills the entire container. It takes up that shape and volume of whatever you put it in. So it doesn't have that definite volume. And these particles are very far apart and they move around randomly. And so there are not many intermolecular force interactions. And so these all behave the same. And this we cover in gas laws. Then if we look at our liquid state, because it has a definite volume, right? It doesn't take on the volume of the container, but it does take on the shape. And that's because these particles right here are constantly moving. They're close together, but they move past one another. And so IMFs are constantly breaking and reforming. So they will have a big effect on the property of the liquid when it boils, when it melts. However, those forces keep breaking and forming, breaking and forming. These have more kinetic energy, so it's able to do that. looking at the solid state, it's going to, these particles will all be in a very definite shape and a definite volume that has nothing to do with its container. And they're all arranged in a highly ordered fashion. And they're close together and in a regular pattern. So one particle will have the same neighbors around it without that changing. And so that means that the IMFs have a really strong impact on how this particle or how this solid behaves. And they stay constant. And that lends to their strength. So what we're going to do in the next, couple lectures is I'm going to walk through first just a few things about solids, and then we'll walk through the liquid state. And we've already discussed gas particles. So let's start with solids and walk through a few things about these. I'm just going to go through the types of solids, and you can assess their intermolecular forces based on the molecules that make up the solid. And since they won't be moving or changing much, we won't focus much on their properties. We'll focus more on liquid physical properties. But just so we're all on the same page of the types that exist, we've got ionic compounds, which form ionic solids. And so these are going to be ions that are actually in a solid state interacting with each other. So these have really strong interactions because there's actually ionic bonds occurring between each of these particles. They have full positive and full negative charges. So there's strong interactions. It's basically just ionic bonds rather than intermolecular forces. We also have molecular solids that are composed of individual molecules that arrange themselves very regularly. And water does this, and they actually form a kind of tetrahedral arrangement with other water molecules. And so this isn't really a bond, it's more of a showing placement. And this structure right here does not have ionic bonds, but it does have strong intermolecular forces because these hydrogen bonds that exist between, I guess this would be drawn like this, that exist in between the molecules stay constant. They don't break and reform, and so they're very strong. And so this crystalline solid is kind of held together by these strong IMFs, whereas our ionic compound crystalline solid was really held together by ionic bonds. So if we think about this, if one is being held together by IMFs and the other ionic bonds, I would expect the melting point for this solid to be much higher than something held together by IMFs. And it's true, ionic compounds are going to melt in the 1,000 degrees Celsius range, whereas water is going to melt at like 0 degrees Celsius. And it really speaks to the difference in strength between an actual bond and an intermolecular force. Other types of crystalline solids are network solids. And so these are going to be solids that are composed of covalently bonded atoms that are actually, instead of arranged next to each other, are actually bonded with one another. And so here's silicon oxide, which is a network of covalent bonds that exist in the solid, and they arrange in a highly ordered fashion. So again, this solid's being held by covalent bonds, and so it will not melt at a low temperature compared to something held together by intermolecular forces. We have metallic solids, and these are really just a lattice of metal ion or metal atoms, right? So we just have copper atoms, and you can think of these as being the nuclei, which are positive, of our copper atoms arranged in a pattern with one another, and there's being this sea of electrons around it that kind of move freely because the electrons on one atom will get so close to the nucleus on another that it'll actually be attracted to all the other ones. And so we just kind of see this as this large cloud of electron density around the nuclei of copper atoms. Now, while those compose crystalline solids, we also have amorphous solids. These don't have a regular arrangement of the particles. They can be formed when things cool very quickly to form a solid. And so they don't have a regular crystalline formation. Instead, they kind of look messy. They intertwine. The molecules intertwine with each other. They don't form a very regular pattern. Large covalent molecules, you will usually be amorphous solids because they'll get in that intertwined. And a few examples of this are like rubber or plastic or even glasses like this.